Let's imagine that we have a table designed in the following way. As we can see, the data redundancy is present in an unnecessary way. In a table like this, the importance of not having this type of error is not significantly present, but in a large tables, it can generate different types of anomalies, whether in the insertion of data or deletion of data. Given a concrete example, think that you want to enter 1,000 records of students. Since we will manipulate one by one of the fields in each record, if each field is not correctly entered, or there will be an inconsistency in the data, therefore we find anomalies in the insertion. In the same way, if the update, we will manipulate many records which, having the same information in several columns, we will require multiple updates. So, if these updates are not properly done, will produce an inconsistency in the data once more time. The elimination of a column or field produces a series of many changes which affects the database in its entry, many times leaving the information inconsistent. So, to solve this type of anomalies and eliminate the redundancy of the data, the process of normalization of database, which we will proceed to explain, help us. First of all, we need to know what is a database and what is its importance. The databases are a fundamental element in the computer environment today, and they have different applications in a virtually or all fields. They are useful for any discipline or area of application in which there is a need to manage data. We understand a database, a set of data structured and stored in related tables in a systematic way in order to facilitate its later use. To create a database, first we need to design it. So we have 4 phases to design the database. The first phase is the requirement analysis. In this phase, communication with the client takes place to know the information system and identify the design's needs, the requirements of the database. Said information, we can obtain it in different ways, through user stories, interviews, meetings, etc. Then we have the conceptual design. The conceptual design includes the creation of a schema or conceptual model of the database. This model is independent of the physical considerations, including database management systems, the language programming, and the different hardware platforms. So, also, the non-technical users should understand the schema. So, it should not contain details about how the database will be implemented, but it must be detailed in terms of the nature, structure, and meaning of the data. During this phase, database designers often create what is known as the entity relationship model or diagram to help them visualize the database. This diagram identifies each entity, also known as the relationship or table in the database, as well as the relationships between the entities. Basically, the diagram is simple enough to allow database designers to learn and understand the basic concepts, but detailed enough to help them develop complex applications. Then we have the logical design. The objective of the logical design is to transform the conceptual scheme into a specific data model for a given database management system. The logical design can be done manually or automatically, in some cases, through the case tools from a conceptual design. In any case, the end result is a set of data definition language commands, which can be used interactively or as part of a computer program to create the database. Finally, we have the physical design. Physical design is the process of physical implementation of the logical data model in a database management system. It includes choosing the specific file structures in which to store the tables or relationships of the database, and ensuring that relationships can be accessed quickly, efficiently, and safely.
Database normalization is a process used to organize a database into tables and columns. The idea is that a table should be about a specific topic and supporting topics. By limiting a table to one purpose, you reduce the number of duplicate data contained within your database. This eliminates some issues stemming from database modifications. To achieve these objectives, we'll use some established rules. As you apply these rules, new tables are formed. The progression from unready to optimized passes through several normal forms. There are three normal forms most databases adhere to using, but there is a fourth which we can use given our database is still not normalized after already having complied with the third normal form requirements. As tables satisfy each successive database normalization form, they become less prone to database modification anomalies and more focused towards a sole purpose or topic. There are three main reasons to normalize a database. The first is to minimize duplicate data. The second is to minimize or avoid data modification issues. And the third is to simplify queries. As we go through the various states of normalization, we'll discuss how each form addresses these issues, but to start, let's look at some data which hasn't been normalized and discuss some potential pitfalls. In general, each table should have only one purpose. Having the table serve many purposes introduces many of the challenges, namely data duplication, data update issues, and increased effort to query data. There are three common forms of database normalization: first, second, and third normal form. But in this case, we also consider a fourth, which is the Boyce-Codd Normal form. The forms are progressive, meaning that, for example, to qualify third normal form from a table must first satisfy the rules for a second normal form, and second normal form must adhere to those for the first normal form. To begin, we have the first normal form. The first normal form expects you to follow a few simple rules while designing your database, and they are: there only have to be single-valued attributes, which means we should not have an attribute containing multiple values. The attribute domain should not change. This is more of a common sense rule. In each column, the values stored must be of the same kind or type. Each attribute and column should have a unique name. If one or more columns have the same name, then the database management system will be left confused. Finally, the order in which you store data doesn't matter. Here is our table with some sample data added to it. Here we can see an example of a table that satisfies the first normal form, since it has atomic or single-valued attributes, and the names of columns don't repeat. By doing so, although a few values are getting repeated, but values for the subject column are now atomic and for each record or row. Next, we have the second normal form, which, for a table to be in the second normal form, it must satisfy two conditions. First, the table should be in the first normal form, and second, there should be no partial dependency. But what is a partial dependency? For this, first we have to understand what a dependency is. For this, we will use our table. Let's take an example of a student table with columns student ID, name, register number, branch, and address. In this table, student ID is the primary key and will be unique for every row. Hence, we can use the student ID to fetch any row from data from this table. So we can say that a primary key for a table is the column or a group of columns composite key, for example, which can uniquely identify each record in the table. I can ask for a branch name of student with student ID 10 and I can get it. Similarly, if I ask for a name of student with student ID 10 or 11, I will get it. So all I need is a student ID and every other column depends on it or can be fetched using it. This is dependency and we also call it functional dependency. Now that we know what a dependency is, we are in better state to understand what partial dependency is. Let's create another table score to store the marks obtained by students in the respective subjects. We will also be saving the name of the teacher who teaches that subject along with the marks. In the score table, we are saving the student ID to know which student marks are these and subject ID to know for which student the marks are for. Together, student ID plus subject ID forms a candidate key for this table, which can be the primary key. How can this combination be a primary key, you may ask? See, if I ask you to get me marks of a student with student ID 10, you can get it from this table? No, because you don't know for which subject. And if I give you subject ID, would you not know for which student? Hence, we need student ID plus subject ID to uniquely identify any row. But where is this partial dependency? Now, if we look at the score table, we have a column named teacher, which is only dependent on the subject. For Java, it's Java teacher, and for C++, it's C++ teacher, and so on. Now, as we just discussed, that the primary key for this table is a composition of two columns, which is student ID and subject ID. But the teacher's name only depends on the subject, hence the subject ID has nothing to do with student ID. This is called partial dependency, where an attribute in a table depends on only a part of the primary key and not the whole key. How can we remove this partial dependency? There can be many different solutions for this, but our objective is to remove teacher's name from score table. The simple solution is to remove column teacher from score table and add it to the subject table. Hence, the subject will become subject ID, subject name, and teacher. And our score table is now in the second normal form with no partial dependency.
The third normal form. The requirements for the third normal form are that the table should be in the first and second normal form. Also, it should not have any transitive relation. For example, our primary key in this table is composed by score ID and student ID. So, let's check the second normal form. Now, subject ID depends on the primary key. Mark depends on the primary key. Exam name depends on the primary key. And total marks depends on the primary key. So, this table satisfies the second normal form. But this table contains transitive relations. So, what is a transitive relation? A transitive relation is when the dependency relations are not direct. For example, in the table, subject ID directly depends on the primary key. Marks directly depends on the primary key. Exam name directly depends on the primary key. But total mark doesn't. Why? Because total marks directly depends on exam name. So if exam name depends on the primary key and total marks depends on exam name, we can say that total marks depends on the primary key. This is a transitive relation. To fix this, we divided the table. Now, let's check if our new tables don't have any transitive relations. Our primary key is still composed by score ID and student ID. Subject ID directly depends on the primary key. marks directly depends on the primary key, and exam ID directly depends on the primary key. So there isn't any transitive relations. Now, let's check the second table. Our primary key, exam ID. Exam name directly depends on the primary key, and total marks directly depends on the primary key. So there isn't any transitive relation. As we can see now, our both tables satisfy the third normal form. The Boyce-Codd normal form is between the third and fourth normal form. The requirement for this form is that the table should be in the first, second, and third normal form, and that in any dependence relation, the primary key should be a superkey. For example, for the relation AB, where B depends on A, if B is a primary attribute, A has to be a primary attribute. So, let's check this table. Our primary key is composed by student ID and subject. Professor directly depends on all the primary key, so it satisfies the second and third normal form, but not the Boyce-Codd normal form, because one subject could be taught by more than one professor. So there is one more dependence relation. Subject depends on professor, but professor is a non-primary attribute, and subject is a primary attribute. So this table doesn't satisfy the Boyce-Codd normal form. To fix this, we divided the table. So let's check if the new table satisfies the Boyce-Codd normal form. For the first table, registry is our primary key. Student and PID depends on the primary key, so this table satisfies the Boyce-Codd normal form. Now, for the second table, our primary key is PID. Professor and subject depends on PID, also subject depends on professor, but subject as a professor and non-primary attribute, so there is no problem and the table satisfies the Boyce-Codd normal form. To normalize a database, we usually use the first three normal forms, and sometimes the Boyce-Codd normal form. But there are times when someone designs a more complex database that requires higher normal forms like the fourth and fifth.
Having concluded with the first part of this presentation, which first talks about the database design topic and its phases, explaining which are the steps we have to follow, and then moves on to explain database normalization, presenting the first, second, third, and Boyce-Codd normal forms, which are as well steps that we follow in order to achieve a proper and efficient database design, mainly considering entity relationship models. Now, we will move on to the second part of this presentation, which is about the paper. The paper we chose has by title Database Normalization Design Pattern. This paper identifies the problem of finding the key of a relation in the process of normalization. Regularly, when we normalize, it is difficult to correctly identify which column should be the key of the relation or which column should be the key for the whole table. For example, this would be a really basic table of our project that is wrongly designed. We can't know for certain which is the primary key, which are the keys of the relationship, which column is related to which other column, and we couldn't properly identify the registers. So now we will move on and normalize the table and also find the keys of the relationship. The paper proposes a tabular approach algorithm. For example, for the functional dependency R comprised of A, B, and C, where A leads to B and B leads to C, we proceed to divide them into a table with columns marked left, middle, and right. In the left column, we put all the columns that are to the left of the relationships, for example A. In the middle, the ones that are both at left and right of the arrow of the relationship. In this case is B. And in the right column we put C, because it's at the right end of the relationship. The validation of this algorithm is by applying it to any table of a database. In this case, we will use the tables of our project. We begin with the menu table. The menu table is comprised of product ID, description, and price. With product ID, we can find the description and also the price. So the relationship would be A leads to B and A leads to C. And we proceed to divide them. Since A is both at the left of the both relations, we put it on the column marked left. B is at the right, so we put it in the right, and C also in the right. In this case, there would be no middle column. So we proceed to calculate the closure using the algorithm. A of 0 is A. This means that with the column A, we can get to column A. A of 1 is A and B. So using A, we can get to the column A and to column B. Moving on, A of 2 is going to be A, B, and C. A of 3 is going to be A, B, and C, and it starts to repeat. That means we have found the closure. The closure in this case means that A leads to A, B, and C. This means we have successfully found the key of our table. In this case is product ID, which will be the primary key of our table, since with it we can find the description and the price of any item in the menu table. Next up, we have another example using the table order detail. In this table we have an order ID, we have products, and we have a quantity. The relationships here are that with an order ID we can find the products, and with the products we can find the quantity. In this case, the columns are going to be divided in left, middle, and right, since products can be both at the right end of the relationship and both at the left end of the relationship. The algorithm dictates that we begin with the left column, so we start to calculate the closure of this column. A of 0 is going to be A of 1 is going to be A and B, A of 2 is going to be A and B, and it starts to repeat. Yet we cannot get to the column C. This means that A cannot be a valid key for our relationship. Then we proceed to use the same algorithm, but with the column A and B, both left and middle columns. So we proceed to calculate the closure. AB of 0 is A, AB of 1 is AB, AB of 2 is A, B, and C, A, B of 3 is A, B, and C, and it starts to repeat. Using both left and middle columns, we can get to all the columns in the table, and that means that we have successfully found which should be the key of our relationship. In this case, we have a composite key of the columns order ID and products. That will be the primary key of the relationship, since these two columns combined can successfully identify any register in the table. After normalizing and finding the keys, we end with our tables after normalization. We have a table for the orders and another one for the payments. Each of one has the primary key and a foreign key if it is necessary. The authors have concluded that applying this algorithm is really effective. We can successfully find whichever key of a table with very low effort and in a really low time, which makes the design of databases much easier. Also, the authors have concluded that the columns that are on the right end of the tabular approach will never be able to form a candidate key, since they are not prime attributes. This complies with the norm for the normalization. And with this, we can successfully take our database to the Boyce-Codd Normal form and have efficient relationships, non-redundant data, and coherent relations. With this, we have concluded our presentation of database design and database normalization, presenting the paper Database Normalization Design Patterns. We hope you understood the topics we covered throughout the whole video, and if you have any questions, do not hesitate to make them now. Thank you for your attention.